right. Howdy, everybody. Thanks so much for coming to see our presentation. I'm Stephen Goodman. I'm a leader in our Amazon Active Defense program. Super eager to chat with you today about how we create and apply threat intelligence and how that creates continuous protection in the cloud for every customer automatically. Tom?
Yeah, hi, my name is Tom Scholl. I'm a Vice President Distinguished Engineer in our infrastructure organization. And over there, I focus on our global network infrastructure, as well as DDoS defense and threat deception technologies.
Awesome. All right, so just a quick show of hands around the room. Who here has actually been on the front lines of responding to real-world threat activity in your environment? Okay, awesome. All right, great. Thank you so much for everything that you do for your users, your organization. You're really the reason why we invest in everything that we're going to be talking about today, from analysis to technology to mitigations. So we've got three big themes that we're going to go through today. First, what we're seeing inside AWS, the visibility and telemetry that we have to monitor our networks and, again, protect every customer. We're going to be talking about what we see outside on the broader internet, the threat activity that we see and respond to today. And then the third is where those two things meet. Some deep dive examples on actual scenarios where we've used our threat intelligence to protect customers and even shape the broader internet environment. So we'll start with some of the sensors and visibility that AWS uses to protect against threat activity. Big caveat, these are internal AWS processing systems and technology. They are not AWS public services that you can buy and use today, though much of what we've built here does, in fact, build on top of the public services that you know and love today, EC2, S3, et cetera. So I'm going to turn it over to Tom as a veteran network engineer to walk us through some of the network telemetry that powers our threat intel work today.
All right, so one of the things that we built several years ago is MadPot, and it's basically our honeypot system that exists across AWS regions and runs on EC2 instances. And it basically looks like a very vulnerable server. It runs a variety of services on it. It's a higher interaction honeypot. And one of the things it does is it captures those sorts of interactions from clients on the internet connecting to it. It logs what kind of interactions it has, and it does analysis on it. And what we do is we take that data and we use it in various ways from a detection perspective, and we feed that into other AWS security-related products from a defense perspective, as well as we use the data that we collect from it for any sort of threat actor disruption work. And so when you look at MadPot, this honeypot that we have out there, there's a variety of different kind of ways to interact with it. And you think of kind of one basic one is, well, what about just scanning activity? So that could just be things from ping sweeps, things like that, all the way to, let's say, scanning for a particular port number. And this is where it actually kind of gets a little bit interesting, because if you think about, well, let's say all of a sudden we see a particular destination port getting scanned heavily on our network. Well, that kind of sounds very interesting. Well, why is somebody scanning that port? What particular service exists on that port? Is there a known CVE? Is it something new? So that's one of these things that we want to kind of pull the thread at to actually kind of figure out, well, what's going on here? Why is there certain interest on a particular port? And that could bring us to something that could be potential zero-day or something else. There's other things that we see too. For example, if we see scanning activity that comes from a very specific part of the world or a specific ASN or a certain set of networks. For example, we once saw a particular broadband networks all of a sudden start scanning very heavily. And we're like, well, what's really interesting about that? Like, could it be that that particular broadband network deploys a certain type of router in their network and it has been compromised and it's being used for scanning? So it does actually have insights just in the scanning telemetry on its own. Another one is the scanning and exploitation type behavior. And this is where MadPot really, its high level of interactivity and its logging visibility really helps, because you can actually see what are people scanning and attempting to exploit. Is this a known CVE? Is it something potentially a zero-day, something we've never seen before? But getting that kind of rich data of actually what are people attempting to send at it and interact with it from a request query perspective gives us that level of insight. And finally, MadPot could go a little bit further, right? It can actually not just get these scanning requests that may come in or exploitation attempts, but as part of its high interactivity, it can actually go and say, okay, someone is actually trying to get me to download this malware. I'll actually go and download it, and I can detonate it and do the analysis of it. And so it can actually have that level of taking a little bit further to really see what is someone trying to get the honeypot to do. So interesting area. So we've had MadPot for several years, and we've only talked about it publicly in the last year and a half or so. But a few years ago, we decided to pivot and actually look into the world of DDoS. And so MadPot has some interesting applications when it comes to the DDoS area, which is an area I particularly focus in. And when you kind of look at DDoS, there's really kind of three pillars. It's kind of three different infrastructure ways DDoS really occurs. And the first one is a common one, is botnets. And so in the case of a botnet, it needs to propagate, it needs to scan, it needs to spread. And so in this case, MadPot will receive these scanning and exploitation attempts. It'll go and get the malware wherever it was instructed to download it. It'll detonate it. It'll analyze the malware and say, okay, here's a command and control server. Since botnets are typically driven by these, it can identify the command and control server, if it's a DNS name, its IP address, its port, and then it could then actually connect to it and simulate that it's basically a botnet client and actually extract that telemetry of botnet attack signals going through it. And then actually go a little bit further to say, well, if this is a known botnet, we verified it, we can fingerprint its C2 protocol, we can then generate an abuse report to wherever it's hosted in the world, whether the domain register, as well as the IP address, wherever it's particularly hosted on an ASN or hosting provider. Another part with DDoS is layer 7 attacks. And so commonly with layer 7 attacks, also known as HTTP request floods or application floods, the way that they're typically architected is that they will go and have multiple machines that use proxies. And what we mean by that is like misconfigured squid, open proxies on the internet. And that's when, if you ever see on the target side of a DDoS attack for layer 7, you're typically being hit by individual open proxies generally, and sometimes private proxies as well. But in this case, MadPot can simulate that it's an open proxy, and it could get on the list that actors used and share around, and basically they'll end up using MadPot as an open proxy, and we can actually see what is being targeted, we can identify the target, and we can see the actual true source of what's actually generating the attack in this case. And then we can go and engage with that particular ISP that's actually the real true source of that layer 7 attack, and we automate that workflow to generate those abuse reports outbound. Finally, there's kind of a classic attack method, which is with source IP spoofing. And this could either be source IP direct floods, where the source IP is spoofed to something else other than the true origin IP, or amplification reflection attacks. In this case, MadPot can act like an amplifier reflector, where it could be running traditionally in a lot of these types of attacks. You'll see open DNS servers, misconfigured NTP, chargen, memcached. So it could be running these sorts of services on MadPot, and it'll get on these amplifier reflector lists, and then we can see that traffic come into our network and actually see, well, we're in our global network, as we do run a large network, over 5,000 unique ASNs we pair with globally. We can actually see where the spoof traffic's coming in from a router and interface perspective, and then engage that particular network. Another source of telemetry is from our network infrastructure itself. As I mentioned, we have a very large network that spans the globe. Our routers themselves generate and emit their own kind of telemetry. And so that could be NetFlow or SFlow records that come out of a router. And typically that's sampled one out of every N amount of packets. We send out one of these records. And that kind of metadata that gets shared here includes things like the router identifier, so we know which one, source and destination physical interface, which is really useful to know which particular network you connected to and you saw it from them. In some cases also, if we're at an internet exchange, we can actually get the source MAC address so we can know exactly which particular peer or participant on an exchange sent it. Source and destination IP, protocol, source and destination port, and then some amount of packets or bytes counter. And so that's really useful for us to really not only just operate and manage our network, right, and do simple traffic engineering capabilities, but it's really useful for actually seeing some of the patterns of certain sort of abusive and scanning behavior. And so an example of that might be one-to-many, right? So if you're looking for heavy scanning activity, you'll see that one single source IP talking to lots of destination IPs, particularly with maybe a specific port as well. You can also use it for amplification reflection type attack detections, certainly when it's one source IP, or in some cases we see some people who will actually spoof entire /24s at a time to basically create this kind of scattering effect of attack traffic. And then finally, the geographic location is interesting too, because we do run this global network and we do connect to so many networks directly, we can actually see and look and say, wow, this particular port from a specific pair, we're seeing a lot of traffic coming through it. It could be something anomalous, it could be something interesting. We could zoom in on it and actually say, what is it about this particular network and this location that we're seeing ingressing our network? Another part too is, well, we expect MadPot to be connected to from different clients over the internet. What happens if something from EC2 connects to it? It could be potentially accidental, but if it's something malicious, we actually automate a workflow where if we see that sort of connectivity and negative behavior from an EC2 instance, we actually automate a workflow with our trust and safety team where we go and reach out with the customer and take any sort of mitigating actions as required. So another part too that's kind of interesting is we do have a lot of IPv4 and IPv6 address space, but not all of our IP addresses are actually allocated to customers or a service. They just haven't been allocated yet. And what's interesting is when you look at that traffic, you can see traffic going to certainly what's allocated, but what about traffic that's going to things that's not allocated? Why are they talking to IPs that there's no service behind them? And so that kind of raises an interesting question. I'll hand it over here back to Stephen to talk about that in a bit more detail.
Yeah. So we've had the opportunity to do some really cool analysis specifically on traffic that interacts with both MadPot and our unallocated IP space. And so when we compare these two data sets, the comparison itself gives us a whole new lens of intelligence. So when we look at the circle on the left, the blue circle, that is all the traffic, the percentage of traffic that we see interacting with MadPot. On the right-hand side is, in the pink circle, is everything that we see interacting with our unallocated IP space. And so you'll see that there's a big overlap between those two things. And so that's about 21% of what we see coming into our network hitting these sources. And within that, you see a large yellow circle of exploitation attempts that are coming from those sources talking to both of our sensors. And so I want to be super clear, these 5%, these are exploitation attempts. This is not port knocking or probing or some sort of neutral mapping activity, actual attacks. When we look at just the interactions with our unallocated space, we also see about 80% of those sources have abuse reports submitted against them to various third-party services. So when we put all of these facts together, that a source is communicating with MadPot, that is communicating with our unallocated IP space, and it has abuse reports, we actually can preventatively protect customers by rejecting traffic from these sources before any payload ever actually makes its way to an AWS customer. And so combining sensor data in this way, we actually create intelligence for both reactive detection as well as proactive prevention. Okay, so we've talked through a variety of different sensors that we have and the way that we can combine them. We've got these multiple perspectives. So what are we actually seeing out there on the internet outside of our network from threat actors? The top technique, far and away, is mass vulnerability scanning. This is really where threat actors are going across broad ranges of IP address space, looking to monetize or covertly control vulnerable resources that they discover. So this has been going on for years. As network bandwidth, data centers have grown, and really as there's been development of specialized high-speed scanning software like ZMAP and MassScan. So we consistently see about 15 to 20,000 external IP addresses attempting to exploit vulnerabilities across the global AWS network. This is a really dynamic set. About 12% of the IPs that we're seeing are turning over every 3 minutes. So thinking about that dynamism and what is the actual driver of the threat activity, it's not sufficient to get a daily threat intelligence dump or even an hourly threat intelligence dump. We want to go faster to be able to keep pace with what we're seeing occurring out on the internet. So at the same time, we do tend to see clustering across ASNs and particular CIDR blocks of around the /24 size. And when we see these patterns, that's a really good indicator, hey, there's actually threat-controlled infrastructure at this particular moment in time that we may be able to hone in on. So we also see network devices from a variety of vendors, very highly targeted. This will be everything from remote code execution, CVEs, to denial of service attacks, to even credential stuffing, trying to take advantage of default credentials or credential leaks to take over the devices that actually manage network traffic themselves. Speaking of credential stuffing, that is also a threat technique that is alive and well. Even with MFA and passkeys becoming more popular for individual users, we see a lot of SSH and RDP credential stuffing, threat actors attempting to take over these core remote administration services and get access to hosts. And then it's not just about 0 days. Sometimes it's about the 1,000 days or sometimes even longer. We see CVEs that were disclosed in 2009, over 15 years ago, still actively being attempted against our MadPot honeypots. So for protection in the customer-controlled space, patching, MFA, zero trust network architectures, those remain key practices. So I'm going to turn it over to Tom to actually go deep on an example of how quickly threat actors will take advantage of going after newly disclosed vulnerabilities.
So I'll walk you through a particular thing that happened back in October 2024. And back then, there was a particular web hosting control panel that was out there. And it by default, lived on a very specific TCP port. And so right around October 23rd, there was an RCE that was reported regarding this particular piece of software. So you could remotely basically get root on whatever thing was running this. And so that came out. And within a few days, and over this period of time, there was a number of scanning activity that we picked up on the MadPot side, looking at this particular port and trying to interact with it and exploitation behavior. But what was really kind of notable was that on October 28th, it was reported that there was a 5 terabit botnet DDoS attack that occurred. And so that got our attention to say, wow, what's going on here? And so diving into that and looking at some of the sources of this kind of botnet attack, and the reason why that's kind of notable is that typically when you think of botnets, there's kind of a wide spectrum of, on the low end, it's in the tens of gigabits per second. In the medium end, it's somewhere around the middle, right around in maybe 100 gigs, maybe several hundred gigabits per second. And then maybe a few times a year, like a botnet will eventually get to like the single low terabits per second range. So to see something that all of a sudden came in with 5T was kind of interesting. That kind of lined up with what happened with this particular vulnerability that was reported out there. And what was interesting was typically with a lot of the botnets, it's usually IoT, residential, DVR type devices. But in this case, this was primarily comprised of dedicated hosted VMs that were contributing to it because they were running web servers and had this web control panel on them. And so we saw that. I saw that pretty large attack. And it really kind of raised some questions as to like, hey, this thing goes public, people are going to jump on it. And it's not just the DDoS folks who are trying to build a botnet there, but we also saw this leveraged by folks trying to do crypto mining and just generalized SSH kind of backdooring. And so here, give you an idea kind of what MadPot saw in this period of time. Here's one example where DDoS malware is trying to be exploited. When this is an actual capture of a MadPot interaction where you can see it trying to basically download a shell script, execute that shell script. If you execute that shell script, it'll download some binaries, and it'll try to execute it, and that's the actual DDoS malware botnet software. Another one, crypto mining. Whenever you see XMRig, it's usually kind of a dead giveaway what's it up to. So that was propagating as well. We also saw cases where SSH keys, so authorized keys being updated so somebody can get into it. And looking on the forums online of people who were kind of going through this and were impacted by it externally, it was interesting that people were finding machines where it had DDoS, crypto mining, and they were backdoored as well because they were all kind of tripping over each other, all these different actors trying to scan for it. I think another aspect too is here's what we saw from this is kind of an excerpt of our MadPot botnet C2 tapping infrastructure, where it basically shows here's the C2 IP address, here's the particular TCP port that it's living on, here's the botnet C2 type based upon fingerprinting the actual protocol. In this case, it was MuBot that generated that attack, and the target address, and gives us kind of a timestamp. And so that's kind of what we see on our end when we actually kind of look at the C2 feeds going out. But I think what's kind of really cool about this is if you kind of start with this vulnerability going public and people start scanning and their interactions with MadPot, is we see that initial scan, that one TCP session, right, with that HTTP request that goes through there. We collect that data. And then the next part is, one of the things that we have in our system that we've talked about before, a system called Sonaris, is we can detect that sort of mass scanning, and we can actually block that mass scanning behavior when it's going across a wide set of our addresses in our network. So that protects customers from any further scanning from those particular resources. The next thing that we do is, well, we've taken this botnet malware, we've detonated it, we know who the C2 is. Do we want anyone from AWS EC2 to be able to connect to that C2? Probably not. We actually impair and prevent that connectivity from occurring. So if there was any kind of infection, it would not be able to contact that C2 and actually get any sort of attack commands. As well as if we do see a customer actually trying to talk to that C2, our trust and safety team reaches out to them to notify them that, hey, you need to take a look at this. And finally, we actually go and this is really for the good of the internet as a whole, where we actually go and reach out to the hosting provider where that C2 is located, and any DNS domain name that could be associated with that infrastructure with an abuse report. So I think it's pretty cool that that one individual connection, that one exploitation attempt triggers all these other operations automatically behind the scenes. So we've talked a little bit about kind of malicious vulnerability scanning in depth, and but we did talk a little bit about the DDoS part, and so kind of giving the idea of like what's going on in the threat landscape, since we're going to talk about some of these topics. Kind of give you a little background on where DDoS is. If you look back towards like the 1990s to into the 2000s, spoofed type of source IP attacks were really common. That could either be a direct spoofed flood where the source IPs are randomized and it's maybe a SYN flood. But one of the more common ones is UDP amplification and reflection, where it's basically the source IP who's launching the attack spoofs the source IP of the actual target, sends it to amplifiers and reflectors, and then sends a large amount of traffic to the target. And that was really popular in the late 90s into the 2000s. Around the 2010s, things kind of changed up a bit. First of all, there's the rise of booter or stressor services, where you don't really need to know how to learn how to launch a DDoS. You can pay somebody else who has a storefront where you can do that, and paying crypto and things like that, where you can then specify your target. You have a certain amount of resources allocated to you. So the rise of those types of services, as well as botnets. So Mirai, Gaffiget, later on MuBot, and a variety of other variants come about, and those particularly target IoT type devices to launch these attacks, and that really gets popular in the 2010s. In the last several years, we've actually seen, I would say, a growth of layer 7 and application and HTTP request floods, and that's basically where it's a different style attack. You're not focusing on network congestion or network exhaustion. You're really focusing the high request load on the web server or maybe the CDN, but ultimately, in a lot of cases, the actual origin behind it. And so layer 7 attacks are really interesting because they've evolved over the last several years. To give an idea, we kind of talked about this a little bit earlier. The layer 7 attacks, the way that infrastructure is set up as a threat actor, will get one, multiple, sometimes dozens. We've even seen up to 100 what we call proxy drivers. And these are machines that pretty much build identically. They load the same Node.js, because a lot of the DDoS attack tools are actually Node.js tools on them. And they basically feed it with a proxy list, right? And so they can get these off the internet. There's an open proxy list. They usually have maybe 5,000 to 10,000 of them at any given time on the internet. In some cases, they may dip into what we call private proxy networks, which are typically you have to pay into, and that could give you access to residential nodes or data center proxies, which are a little bit more performant than these open proxies, mainly because these open proxies are being abused by so many people for a variety of things such as DDoS, cred stuffing, random scanning, malicious scanning, and so they don't always work that reliably. So this is really kind of the infrastructure behind how a lot of the layer 7 request floods are basically orchestrated. Now, it used to be that with a lot of the layer 7 request floods, it was all about the request per second and driving that up and really trying to exhaust what you could do on the web server. Over the years, there's been a lot of layer 7 anti-DDoS defenses that have come out over time. And so WAFs have been one technique that people have used to do this, limiting how many requests you could do per second for a given source IP, looking for different kind of signatures. For example, one signature technique was with TLS client hello, also known as like JA3 fingerprinting. And for a period of time, that was actually really effective until it became too effective, and then it wasn't. And then that's when it happening was threat actors have decided, well, let's try to change our software, because typically when they build those proxy drivers, they're putting the same version of software in every single box. So the signature was super clear. Now they've actually changed a lot of the software around where now they can do some level of randomization to make that a little bit more trickier. Other kind of innovations from an attack perspective are not just going and doing a get slash, but actually going and trying to do a get slash some kind of random value or some sort of random queries, something that isn't cacheable, something that actually has to go back and hit the origin uniquely and try to drive that load. So it's less about just getting that high RPS, which on the high ends may be in the millions of requests per second, but it's all about how do you evade and actually try to get enough through to actually go after the origin and cause trouble. And then over the last few years, there's been some use of HTTP2. And so traditionally it was, okay, well, HTTP1, you can only get so many requests through. HTTP2 opened the doors in terms of having a lot more sessions that you can run on a given TCP session. And back in 2023, and it became public in October 2023, was the HTTP2 rapid reset attack. And that basically allowed you to have that one TCP session where you can have all these individual HTTP request sessions over them. And you could basically say request for something, and then the client would say, forget about it, cancel it. But the web server's already gotten that request, and so it's going to do that work and respond with an answer that you basically said, I don't care about anymore. So you saw these request floods that were maybe at the top end of a few million requests per second, all of a sudden you're going from 0 to hero to like 50 million, well into like 100 million plus range, right? So it was a pretty interesting amplifier, and so the industry responded back with coming up with more creative mitigations to deal with HTTP2. But it's definitely an area where there's a little bit more innovation because it's a different attack type, doesn't require network congestion type of techniques. So one thing I did talk about earlier here was with source IP spoofing, amplification, and reflection attacks. So it's an interesting one where somebody has to get a host somewhere where they can actually spoof. And most cloud providers, most large hosting providers, and most, thankfully for a lot of good work that people have done over the industry, have made it so that most broadband providers don't allow IP spoofing, source IP spoofing. But there's still a number of kind of smaller hosting environments that you can go to, and you get a dedicated server, in some cases VMs, that still allows spoofing. And so they get these amplifier lists that either they scan themselves or they get provided, and it gives them the list of amplifiers and different services to go and use to basically generate targets to launch attacks to reflect and hit the destination. And so this is an area over the last few years that we've been active in with other companies as well, and to trying to identify what networks are allowing spoofing, have actual attacks leaving from their network, and try to get it shut down. And so what we'll do is we directly engage with those networks when we find them, because we pair with a large set of networks around the globe. We can see the spoof traffic coming in. We can go and report to them. And that reporting is interesting, right? Because at that point, it's you talking to another human, whether it be a NOC or an abuse department or some kind of to contact. And so you try to explain this to say, hey, we saw this packet come out of your network. It was a large amount of packets. It was all one particular source IP to this destination, destination port typically, and try to explain to them to say, can you use what NetFlow data you can have at your disposal to try to figure out where the source is, and either talk to your customer and try to shut it down, apply some sort of anti-spoofing filters. And so frequently we have to find that because a lot of networks aren't really proficient at this, using a picture like this actually helps quite a lot to basically say, look, you're the ISP, I need you to go find your customer behind you that generated this thing, please use your tools to go do that. And so we'll work with an individual, various pairs all over the globe to try to do that whenever we see these kind of hotspots set up, because that's usually a booter or stressor who's basically established some sort of operation at a particular hosting provider, and they'll keep operating until they eventually get shut off. Now, it gets a little complicated though. As you talk with a lot of these external networks, you basically bring this kind of information to them and ask them, well, can you try to find the spoofing? And you get a variety of different answers. And a lot of it comes down to that they're just not really used to these sorts of requests. So a common one is when you send it and say, hey, I saw the source IP at this timestamp going to UDP port 389, Windows C LDAP. Can you go and use your NetFlow data to try to find the source? A common answer is, well, that's not our IP address. We don't announce that to the internet. It's like, I know, it's because the source IP was spoofed. That's kind of the point. I need you to go and actually try to find the source of it. Sometimes we'll send even Amazon IPs are being spoofed when they send to our network, and they're like, well, you made a mistake, that's your IP. I'm like, no. It's been spoofed on your side. We need you to look at it. A common problem is that when they think DDoS, they think destination IP. So they ask, well, what are the destination IPs? I'm like, well, it's to a lot of amplifier reflectors. It's a really long list. If you're fixing a destination IP, you're going to get it wrong. You need to step back there. Sometimes you get kind of interesting results. Like one particular network said, they offered to say, oh, well, if you have a problem with DDoS, you should buy some of our DDoS scrubbing services. Like, no, that's not what we're trying to do. So there's a few other ones. Sometimes they struggle with some of the NetFlow relating tooling, and because it's a different sort of request that they're used to. So sometimes they'll show some of their NetFlow tools. Sometimes they're third parties. We know people at those companies, and we can introduce them and kind of help them to be like, this is how you do a query to find the source. And so that one day I decided to kind of collect some of these bingo, these items here and put them into a bingo card. I've hit all of them, sometimes multiple times. So, but the point is really not to particularly clown on any particular network. It's really more about there's a technical proficiency thing, and it's really about educating, because it's just me and our folks with email clients. We have no authority to make a network particularly stop spoofing. It's all about really trying to inform and try to get to a particular outcome, which is we want to try to get this activity shut down. So it's about explaining and educating to others and teaching them this is how you actually go and find this, and hopefully you can become proficient enough where you can find it on your own. And so it's an ongoing kind of educational thing, and where you want to drive the right behavior, which is if you're a hosting provider, there's no reason why you want to allow spoofing to a particular dedicated host or VM, by default. That is not the right thing. So I'll walk through one particular scenario that happened mid-2024. In this case, this is an interesting case of SIN and SIN Acrifaction. And so back in summer 2024, we saw a large set of source IPs were transmitting a fair amount of TCP SINs to every Amazon IP for many hours at a time. And so it was multiple /24s together, which is kind of unique, right? And it was on 80 and 443. And because usually if there's going to be a web server, those ports would answer if you sent a packet there. What was unique about some of the sources being spoofed, they were all kind of South American ISPs. And the intent here is that they were, instead of doing a UDP amplification reflection attack, they were doing a TCPSin Acrifaction. So that's basically they send a SIN, port is open, they get a SIN-ACK back, and usually a few SIN-ACKs come back. So the amplification factor isn't that great, but you still get something that bounces back. Now, if you were on the target side of this, you would see a lot of SIN-ACKs coming into your network, right? And that's something you want to probably be really careful if you filter that, because that could be legitimate connectivity. So you need to there's some caution that you need to take here. From a size perspective, we saw millions of, I'd say tens of millions of TCP SIN packets were being sent at a given time, usually for hours, like 6-8 hours or so, and then would continue the next day. So it really got us kind of thinking. And one of the things that we also heard from a back channel was that some of these networks that were being targeted had mentioned that a hosting provider who also provides DDoS protection was approaching them afterwards and saying, hey, do you need some DDoS defense capabilities? And so that kind of made us think like, oh, interesting. Oh, who is that network? And so to give you an idea, at a high level, it kind of looked like this, where we saw traffic attempting to bounce off our resources. We talked to a few other network operators as well, and they said, yeah, we see a lot of these TCP SINs too coming from these same ranges on the same set of destination ports. It's like, okay, so somebody out there is clearly spraying all this to try to do this reflection to target it at something. And so we engaged our upstream network where we saw the spoof packets come in from. We talked to them and said, hey, can you trace this back? As they were looking into it, we also said, we noticed there's this one hosting provider. They happen to be a customer for yours too. You may want to take a look at them. And they did, and there was some sort of engagement there. And eventually, it looks like they got filtered, where all of a sudden the traffic stopped. We thought, okay, that's pretty cool. Everything's good. They found the right source of it. But then the next day, we saw all of a sudden it came in from another transit provider. We thought, okay, hey, that hosting provider, they also are behind the second transit provider too. Let's go reach out and talk to our transit provider and maybe kind of point them in that direction to say, you might want to take a look at this. And they do, and eventually it gets filtered and the attack traffic stops. Now, what was also interesting is that particular hosting provider, we actually happened to pair with them in a particular off an internet exchange in some place in North America. And we thought, well, that's really interesting. If we're seeing all the spoof traffic and it's coming from them, how come they never sent it on the internet exchange with us before? Like, we're announcing them prefixes. How come we never saw it? But then we started seeing, after these two transit providers applied some filtering, we started seeing it directly coming into our network where we have a pairing adjacency with them. So at that point, we see the data, it's clear, it's coming in. I can see their source MAC address of their router. I engage with them directly, and they get automated kind of a ticketing system, and they said they're looking into it. And then after that, the attack traffic stopped. And it stopped for quite a while, for several months. It did come back a few months later on through one of the transit providers, I believe, that unfiltered them for a short period of time and then reapplied it. And then we saw it come back on our exchange ports again, engage with that network again. And we did, and all of a sudden the traffic stopped since then. So kind of odd behavior. It kind of gets into another topic, which is suspicious hosting providers. And so one of the things that we see is when we see some of this DDoS activity, whether it's spoofing, layer 7 proxy drivers, C2 infrastructure, we see that there's a certain number of ASNs where this stuff typically gravitates around, all right? And it seems to be very persistent, that these particular networks seem to have a fair amount of it. Same goes for scanning activities too. We see it for amplifier, reflector, proxy scanning, comes from some of the same ASNs over and over and over. In one case, there's one hosting provider had a Telegram channel. We see their employees in there. We also see their customers in there. They're openly talking about IP spoofing, so it kind of seems like they might be looking the other way. And one of the things that we also notice is some of these particular networks, these specific ASNs, they seem to be getting bounced from transit provider to transit provider, from what we could tell looks like due to abuse issues. And so they're getting kicked off and moving to different networks. And unfortunately, like in certain parts of the world, there's a very lively IP transit market. So there's a fair amount of smaller networks that they can go to buy that connectivity. But it's definitely a pattern that we've seen in the last few years where a lot of this stuff kind of clusters around. Let me hand it back over to Stephen.
All right. Thanks, Tom. Okay. So we just learned a lot about the bad activity that we can hone in on just from keeping a watchful eye on our network infrastructure of the backbone links that flow into the AWS data centers. So I'd like to talk about what we detect from looking at a little bit of a higher level telemetry, AWS service interactions, and how we can use that to secure customer resources. So CloudTrail, I imagine you're all familiar with. This is a great application layer audit log of the thousands of interaction types that working with AWS creates. And CloudTrail captures both user-driven workflows as well as automated system interactions, your programmatic stuff, your API calls. So it's a treasure trove of details. It's really a map of who, what, when, and where for every interaction that occurs in your accounts. Right, so you get details like what is the source IP address and user identity of the client caller, what did they actually try to do, what was the event name, event source, really rich details around the request and response themselves, and then a timestamp, which makes everything great, what region this information was logged. So you'll see a lot of the techniques that I'm going to describe in a bit are applied in our public services, like guard duty, like inspector, to give customers direct control into risk visibility and then automation hooks that you can drive whatever custom workflows you want off of the findings from those services. So what do we look for in CloudTrail? One really great signal is we refer to it as IP address affinity. Looking at the actual client IP address, how often does it interact with account A? How often does it interact with service X in account A? How often does it interact with other accounts and other services? And as we start characterizing that, we can build a map of what is normal for this client to be interacting with and what is abnormal and perhaps a little bit unusual. Then, unusual sequences of actions within the management of your AWS account, right? If you look at normal in an account, is it usually used to run ECS workloads, Kubernetes, anything like that? And then one day, you start seeing CloudTrail records where someone's trying to configure simple email service and use that to send outbound messages. Is that normal? I don't know. Breadth of describe actions. Describe is a very common prefix in CloudTrail events where you'll see describe instances, describe tables, describe users, et cetera. So are you seeing this broadly across many different services in your account? If so, that could be a good signal. There's somebody in there trying to get a sense of what access do they have, right? What are the resources within this account? So what about services that your account does not use frequently? Talked about VPNs a little bit earlier. Anonymizing VPN usage, particularly in conjunction with management events in CloudTrail, creating a resource, modifying a resource with an IP address that isn't known to your network or that you can clearly link to a particular VPN service. Again, little unusual, suspect. And then a great indicator for so many different types of threat analytics is just high failure rates. Threat actors need to research, they need to understand what they have access to, what they don't have access to. So when you start seeing lots of 403s, 404s, 500 responses in in CloudTrail or in your service application logs, that's a indicator, a breadcrumb of, hey, something is failing a lot, someone doesn't have access or is doing something unusual. So is this happening across all your users or particular user identities? So none of these things are like a smoking gun, oh, this is threat activity. But when you start seeing them stacked up together and co-occurring, it makes you question, is this really legitimate? So using this new lens on top of the network telemetry that we described, looking at service interactions, let's dig into some actual threat activity that we see in this space. Okay. So many threat actors are not even doing anything particularly sophisticated. They're taking advantage of inexperience, they're taking advantage of mistakes, and they're looking for insecure configurations of apps on the internet. Right? There's a lot of services that are really designed to be run in private networks, or sort of developed over the last 10 years, longer, before Zero Trust really became a popular network architecture. And they don't have super strong authentication controls baked in, or maybe they've been bolted on, and it takes extra work to really get that into like a strong internet exposed posture. So things like databases. Do you have your SQL server, your Postgres, your MySQL with a public IP address? And perhaps it's just protected with a username password combo, maybe even no encryption on the network connection. That's something that can be credential stuffed, and potentially if you have a default application installed there, maybe they're default creds and somebody can get access to your database on the internet. Log search clusters, Prometheus, Grafana, Elastic, really popular, powerful tools for understanding all the data that your organization collects, your application collects. But do you have it secured? Does it have a public IP address? If so, it's possible, hey, unauthorized actor could just hit the APIs like you do and look for whatever information you may have happened to have indexed in that cluster, right? So if there's anything sensitive in there, that could potentially, that's the sort of information that threat actors are looking for. And then analytic clusters like Spark, Hadoop, these are actually designed to execute code that you upload to them, right? Which is just a gold mine for anybody who's looking to, get free compute on somebody else's bill for crypto mining, phishing, et cetera. Right. So I was looking at GitHub yesterday, looking at some popular open source tooling, and the number of readmes that I saw were just like getting introduced to a package. The very first thing, it says getting started, and then immediately under it's like, do not do this in production. Like, how common is open source set up that way of like, here's how to get started, but don't do this. People do it, right? And so you see popular open source tooling like content management systems. I think there are hundreds of millions of WordPress sites out there, some of which are running old versions, might have default credentials, may have their web root misconfigured. Deployment automation systems, Jenkins is a great example, where it has privileged access on your network. It may have secrets to log into other infrastructure that your organization has. And there's a big ecosystem of plugins that you can install that have varying quality and testing levels. So in all of these cases, if threat actors scanning the broad internet discover one of these insecure configurations, they're going to do the bad stuff that we're talking about. They're going to crypto mine, they're going to info steal, cred stuff, the works, right? And we see it every day. So speaking of credential theft and abuse, this is something that is prevalent right now. It's easier to log in to a service than it is to execute some complex attack chain with sophisticated tooling or reverse engineering, exploit development. So because of that, there's a really active black market for credential resale, and where threat actors are incentivized to gather credentials, whether they work or not, whether they're valid or not, and bundle them up, resell them. So we see continually just internet traffic coming into our data centers looking for exposed credentials in well-known locations. About 500 million requests per day, just hunting for whether there's an exposed.env file that might have access keys or username password combos or API keys to a service. That's a lot. In addition to the internet-connected services that might accidentally leak keys, threat actors also target individuals. They're not just targeting services. They might go after, an executive, a help desk person, anybody in an organization that just happens to fall into one of these avenues. So there's a variety of mechanisms for distributing malware just for credential stealing. Phishing, people downloading cracked software because they don't want to pay for a real license for X, Y, or Z, and they find something on the internet and download it, and oh, oops, it's a backdoor. Some threat actors, in fact, will even place ads on advertising networks that you get fed into your browser, and they take advantage of browser vulnerabilities, again, to install info stealer malware. So if any of these mechanisms happen to catch AWS credentials, then you're going to see the things that I was referring to on the other slide of crypto mining, outbound phishing, data exfil, malware staging, right? It's just every time threat actors get more resources in their network, they're just going to copy-paste the bad activity. Okay. So illustrating a quick attack chain of how can pivot from an individual workstation that may be compromised, or laptop, personal device, into your enterprise environment. If you have an individual, you can imagine one of the scenarios I mentioned, maybe a help desk engineer or support engineer gets a phishing email that they download some document with malware staged in it. That malware then is going to be able to scan the memory of that box, look at sensitive files, look at registries, password managers, and then they're going to exfil those creds, either to threat-controlled infrastructure, or in some cases, they might just take over the box and start credential stuffing services directly from there. And so that transition from a individual user's personal device or enterprise device to your service infrastructure, we see the credential stuffing happening, again, at a very high rate, hundreds of millions of requests. And then if they have success with any of those credentials, they're going to keep moving on and try to copy paste that and just repeat the success that they've had. So all of this is supported via evasion via the network, right? Sort of the classic way that many security systems are set up is you have allow lists and you have block lists on your network who can access my private resources. And so what we see is threat actors attempt to circumvent this using VPNs or a different technology stack of HTTP and SOX proxies, where their traffic is going to come from different locations, and they're going to be able to hop from different IP addresses over and over. So this can be repeated via multi-tenant hosters, compromised devices like we've described, which occur in both data centers as well as in residences. The little set-top boxes that you get, or your home cameras, et cetera, like, again, oftentimes connected to the internet. And then this is a highly dynamic space, as we've talked about. We see a lot of rotation here. But it's rarely more than 50,000 IP addresses is sort of like the total amount that we see threat actors able to marshal at any given time. Rarely goes beyond that because threat actors are cost conscious as well. But because it is so dynamic, there's often legitimate customer traffic that is also on these network links, and we don't want to block it, and we don't want to disrupt customer experiences. So keeping up with this dynamism is really the core opportunity here. Okay. So diving into an actual case study of where all of these techniques I'm describing sort of converged into a particular example. This was in late 2024, and we started getting some reports from customers that they were seeing ransom notes in their S3 buckets. Here's a little redacted sample, actual ransom note that we received, where you can see some details being asked, hey, pay us some Bitcoin. If you give us Bitcoin, we will release a decryption credential to you. If you need any help, email this address and we'll work with you. So pretty not good thing to be seeing in your resources one day. As we saw this activity unfolding, and we looked at what's going on, we had actually found all of the keys, the AWS access keys that were being used in this campaign, we'd actually detected as compromised previously, and had sent notifications to customers, hey, we're worried that your key may be exposed, via some of these leak mechanisms we described before. You should rotate, you should take advantage of some different best practices to ensure that your credentials are safe. Again, over the course of a few days where this was unfolding, speaking to the credential black market, we actually saw multiple threat actors at the same time in accounts doing multiple different activities, like attempting to set up EC2 instances to perform crypto mining, as well as this ransom activity, footprinting, outbound, spam and phishing. And so that was indicative, hey, there's some coordinated campaign that's happening here amongst sort of loosely affiliated groups. They're not doing the same thing, but they're using the same creds that probably came from the same access broker. So again, we saw all of this happening, right? The actor tooling, we saw it, we had the detections, we're like, okay, we're gonna block at the network level. Right? Try to stop the pain for our customers because we want to do more. We want to help. We want to make these threat actors stay away from our customers. what we saw is within a single day, they figured out, oh, we're getting blocked at the network, and they broke down their operations. Every single step of their operation, they came through a different IP address, right? So we had to adapt as well. Turned out to be an Indonesian-based actor cell, and like even adding to the frustration here, in some cases we heard reports, hey, they're actually running like a double extortion scam where the encryption keys that customers are paying for don't even work, right? And you get that and then you find out, oh, now we want more to give you the real decryption key. So again, not a good story to go through. So putting all these factors together, we took our detections that we had notified customers about, that we saw of the tooling, and we actually fed it directly into the S3 and identity control planes and data planes to just stop this activity cold, the actual techniques the actors were using for the encryption. And over the course of this, once we had this deployed, stopped the activity 100%, over 900 million attempts to encrypt objects were stopped from this activity. Okay. So that's where this really pays off for customers, is being able to put all of this information together and with the notifications and with the active defense, actually help the customers work through application security issues on their own, where they're like, we're getting notifications multiple times that these keys might be exposed. And so they were able to sit down with their development team and be like, why are these keys leaking? Fix the core issue, go beyond just their AWS credentials, but actually other things that they were concerned about, and ultimately drive real proactive security outcomes from the threat intelligence. And so this is the golden path scenario that we see regularly, and it is really the baseline, and these other threat activities are sort of the anomalous side of things. So really taking this to a scaled idea, we've got other sources of data, but we'd need a longer talk to be able to go through all of them at the depth that we've talked about already. I will quickly call out the security community insights at the bottom of, there are many great organizations, security research organizations, active defense and SecOps organizations throughout the community that share their research, that help go after these types of threat actors. And that is so valuable because they've already synthesized so much of this low-level information and shared very actionable intelligence. So that's huge thanks to all our collaborators in this space that we're able to keep threat actors at bay through the collaboration. So all of these different data sources sort of stack up together. If you've heard of the pyramid of pain, this is sort of the inverse of that, where at the lower level, we have data that is the broadest, it's the highest volume, and it's the closest to the hardware. So it really gives you a picture of what is going on, ground truth. But then data sets towards the top, they're smaller, they have more context baked in, right? And they offer stronger signals of intent behind the interaction. And so using this pyramid of stacked data, we can make these really broadly conditional detections across multiple sensors and do it super fast. So we can look at, hey, everybody that's talked to MadPot, that's attempted an exploit against a Java process from an ASN that is really tiny, that doesn't usually talk to us, that and so on and so forth. And each of these conditions that we add to our detections actually make our detections faster the more specific that we go. And so we're refreshing all of these data sets continually, right? Machine speed, so that we can keep up with the real interactions that are happening in this very dynamic network space. So to give a sense of the scope, we are reviewing over 360 trillion telemetry events per day, which is like a mind-bogglingly large number. That's over 4 billion events per second, a snap of a finger. And from this, we're continually generating active mitigations across the network layer and the service data and control plane that are being pushed out every 3 minutes, right, to disrupt threat campaigns all the time. So it takes a lot of engineering smarts to generate that effect, but what does it really do for customers? One, we stopped malware infection attempts on EC2, over 4 million over the last 12 months. We stopped the exploit attacks that we see in MadPot, hundreds of millions of attacks that we're seeing every day, never reach an EC2 workload. We disrupt botnets, which preventing inbound and outbound DDoS attacks and propagation of malware and vulnerability scanning. And we protect credentials. We actually make it about 30 times harder for opportunistic threat actors to find accidentally exposed credentials, block over 150 million requests per day for all customers. So, a lot of information that we shared with you here today. Really appreciate you sticking through with us and your interest in the topic. As our big wrap up, we invest really heavily in these telemetry and sensors because security is part of reliability, right? We want customer operations to go as smoothly as possible, right? So that means proactively identifying threats that could be disruptive to your operations. And then turning these observations into intelligence at global scale, it really requires data science, right? We need to scale via automation, and automation requires really powerful models that can make decisions that are both precise and fast. We really are keenly interested in intelligence because it's only as good as the actions that follow it, right? And so we choose to disrupt threat activity and make their operations more difficult and costly. And then finally, we talk about the shared responsibility model a lot at AWS. And we also have shared outcomes, right? We're super deeply invested in supporting customer operations. And so by building these complementary controls at the AWS infrastructure layer, allowing you to focus on your unique security controls that are useful for your applications and your users and customers, together, this actually makes the internet safer for everyone. So thank you so much for your time and attention today. Really appreciate your presence. Thank you for coming to Reinforce, and look forward to working with you in the future.